We're going to continue with fixed beamforming. So we talked about the signal model. So our signal model for fixed beamforming is very similar to what we did with signal enhancement, multi-channel signal enhancement, but it's different in terms what we can achieve, what are the assumptions, and what is known. So based on this information, we defined different problems. So the model was like this. So if we have an array, okay, an array of M sensors, this is number 1 until M, and we assume that we have a source, desired source, that comes from a certain direction, theta d, and we assume that we know this direction, we can write our model goes that YMF equals to XF DM F, and actually I can write either cosine theta d or just theta d, whatever you like. Okay? So I can write more generally as theta d because it depends on theta d. The cosine theta d that we wrote yesterday is just to show that for uniform linear array or linear array, we have symmetry. And more generally, it depends on two directions. Also, something that I didn't talk about yesterday, but you are familiar with that. Suppose that we want to work with near-field sources. Okay? So we can also design beamforming, fixed beamforming for near-field sources. And then we will put here some direction and position, okay, and so on. So all this, what we talked throughout this course, don't limit yourself to what I show you, because what I showed you is just examples. But many things can be combined depending on what you want to achieve. Okay, for example, if you have smart glasses, and the source is not from far, but you design your device to pick up signal from near field, close to the person who wears this device, then you need to design, you need to check maybe a near field source, desired source. Okay? So then don't treat whatever there is either in the book or in the slides or what I teach you. This is it, okay? Everything can be changed. Once you understand what is the situation, what are the conditions, you can formulate the model, okay? So be flexible with what you define. Not only what there is in the literature, because maybe someone defined a problem which is suitable for him, but it's not suitable for you, what you want to achieve. Okay, so this is important. Plus noise. So this is sensor number M, and then we can define it by a vector of M sensors, the vector for each frequency F, which we have like XF multiplied with a steering vector F theta d plus vector of noise. And we assume that we don't know any statistics about the signal. If we know about the statistics of the signal, or we can estimate it, then if this vector is a steering vector that will look to a certain direction or to a certain position if it's also in the near field, so it will be adaptive beamforming, what we explained yesterday. So these are the differences. And also regarding the noise. We don't know what is the environment because we designed the device, and afterwards somebody will take the device, the array, to a different environment. So of course, in that environment, we can estimate the statistic of the noise. But then this method is called adaptive beamforming. if we don't estimate the statistics of the noise, we need to make assumptions in the design. So we saw that we have different ways to design a fixed beamformer based on this very limited information. Okay? So our objective is to do fixed beamforming, which means that we find a beamformer that is applied in each frequency to the vector of measurements, which is a vector of length m of measurements. And the question is how to design an optimal something, optimal beamformer. When you reach to a different problem, when you think about what is the best way to achieve something, you need to define what is the objective. Without objective, we don't know to define the optimization problem. Okay? So, because we don't know statistics about the signal, nor statistics about the noise, we need to find suitable performance measures that maybe will be suitable to a real environment. And then we think, what kind of in a real environment, what can we assume? Okay? So we can assume either white noise. About the environment, the noise. We can assume maybe diffuse noise. And of course, we can take combinations of these two noise fields. We can assume that maybe we have an interference from a certain direction. Okay? Directional interference. And so on. Okay? So you need to think, when I design the beamformer, what will be actually suitable or useful in a real environment. Okay? So if we assume that we have white noise, we can try to maximize the signal-to-noise ratio when we don't know any other information. So because we don't know any information on the signal, we need to assume that any signal that will come, that it propagates from that direction, theta d, will not be distorted. So we use, for all beamforming methods, we assume that we know the direction of the desired source, or we estimate it, okay? And then we apply constraint that the beamformer, any beamformer that we will design, will not distort the signal that comes from theta d, from a certain direction. Okay, so it's one, and it's independent of the frequency. This is very important. You see, for example, when we estimate signals, when we talked about multi-channel signal enhancement, of course, also single channel, but I want to limit ourselves to multi-channel. So when we talked about multi-channel signal enhancement, we don't necessarily use a constraint of distortionless response because we try to find a trade-off between signal distortion and noise reduction. So sometimes we try to reduce more noise and we allow for some distortion of the desired signal. With beamforming, we don't know the statistics of the signal. We don't know anything about the signal. We just know that it comes from a certain direction. So we cannot compromise between signal-to-noise ratio or noise reduction and signal distortion because we don't know what is the signal. So we cannot apply or use a constraint that will allow some distortion of the signal. So we use this constraint. that signal that comes from that direction will have no distortion at all. If you have another suggestion for a constraint, you need to think. Is it possible? What does it need? But if there is a signal that comes from this direction, and I don't know anything about the signal, I cannot use correlations between sensors regarding that specific signal. Okay? So in the time domain, we use correlation matrices of samples. In the frequency domain, we use correlations between sensors, relative to the desired source. Okay? So we called it phi x f. This contains information about the specific characteristics of the signal that comes from theta d. And then we have certain correlations that take into account what is the correlation between the desired signal component in a certain sensor and another sensor. For example, the reference sensor. Okay? So this is important information that we don't know. We don't assume that we know, and we don't try with beamforming, design of beamformers, we don't try to estimate it. Okay, so when we don't try to estimate some information, it means that either we don't have the computational resources to do it, or maybe we don't know the environment, or maybe we assume that the performance will not be much improved because we don't want to design filters or beamformers for any environment. So we allow some degradation of the performance because of not knowing the exact environment. Okay, so this is a constraint which we see is different than what we used for multi-channel signal enhancement. In the multi-channel signal enhancement, we use such a constraint only when we talked about distortionless response. MVDR, LCMV, GSC, okay? With beamforming, we have to use it for any beamformer that we want to design. Otherwise, we cannot control the distortion. Maybe the distortion will be such that we don't pick up the signal, okay? Okay, so this is important. Now, concerning under this concern, under this constraint, what can we do? So we can control the amount of noise that is reduced using the beamformer. But we don't know what type of noise we have. We don't know the correlations between sensors regarding the noise source or noise sources. We don't know what kind of environment it will be used for applying this beamformer. So what do? So we defined two different performance measures. One we call white noise gain. This is the narrowband white noise gain, which means how much output SNR can be achieved, or how much gain in SNR can be achieved using this beamformer. So under this constraint, we have that it's simply H okay, so it will be, if I put this will be in the denominator, so I can write 1, okay? And in the numerator, this will be like this, minus 1. Okay, under this constraint, we can write it. You see that in the numerator, I put 1 for such a filter if we obtained it with this constraint. So for a beamformer, we can write something like that. And for the directivity factor, of a filter that we designed under this constraint, we can write it as H F gamma. And this is the normalized correlation matrix of the noise, but for diffuse noise, which we denoted like this. Okay. Now we saw that if we optimize, we find H, beamformer, that maximizes the white noise gain. Okay, so this will be minimal under this constraint, subject to this constraint. So we can design maximum white noise gain beamformer. So we can achieve H max white noise gain. Okay, and this is for, we talk about narrowband, okay? And we can also design a beamformer that minimizes this, minimizes what it's inside. So it maximizes the directivity factor under this constraint. So this constraint, we always use it, okay? So I don't need to mention it again and again. Of course, we don't forget. This, always we apply it, okay? And then we can have H max directivity factor. Now we saw that if we design a beamformer that maximizes the white noise gain, the directivity factor that we'll obtain using that beamformer. So if our objective is to maximize the white noise gain, and we use it and we compute the directivity factor that is obtained with this beamformer, the directivity beamformer will always be larger than 1, larger than 0 dB. And this is a nice result, because it means that if we designed a beamformer with the objective to get maximum white noise gain, which means that we thought to design the beamformer such that it will be used in an environment with only thermal noise, no diffuse noise. Then if in the actual environment there is some amount of diffuse noise, it will not be amplified. The directivity factor is larger than 1. So this is good, because it means that this beamformer can handle also diffuse noise, in case we thought that there will not be diffuse noise in the environment, but if there is some diffuse noise, it will not be amplified at the output of the beamformer. Now, on the other hand, if we design a beamformer that will maximize the directivity factor, which means that we design it offline in advance, and we think that this beamformer with the array will be used in an environment with diffuse noise. And then eventually people take it and design it and use it in an environment with white noise. So then this beamformer is very sensitive to white noise, which means that the white noise gain that we'll achieve using this beamformer that was designed to maximize the directivity factor, it will generate the white noise gain will be very low. It can be minus 50 dB, minus 60 dB, minus 100 dB. Okay? And this is very problematic, because when we design something and we don't know what will happen in the real environment, we need to consider things what will happen in the real environment. So if in a practical case there will be also white noise, and actually there is always white noise, thermal noise, and so on. So this beamformer, the use of this beamformer will create a very strong amplified white noise at the output of the beamformer, which is very problematic. Okay? Not only that, okay, something that is very nice to show, okay, but it's also considered, we talked about robustness not only to the environment that we are not aware of. We need also robustness to inaccuracies in the position of the sensors, because we assume, you see, when we take this, the steering vector, we assume that we know exactly theta d, we know exactly the positions of the sensors in space, because if we don't know, then it's incorrect. This steering vector uses, or we need, the position of the sensors in space. And we also assume that the sensitivity of each sensor is the same. Sensitivity, it means the magnitude sensitivity, the magnitude gain, because what is a sensor? Sensor, propagating wave, for example, acoustic or electromagnetic with antennas, whatever. Sensor, passive sensor, is something that receives a propagating wave and it generates at its output electrical signal. But this transform or gain depends on the sensor. So if you have differences between sensors, the output signal will depend on the sensor, not only on the propagating wave. So there can be magnitude differences, there can be phase differences. You see, your propagating wave will come out electrical wave, that doesn't correspond to the exact phase of the propagating. The electrical signal will not correspond to the phase of the propagating wave. And this is very important because, you see this steering vector, we assume that all sensors are similar, the same response. So the propagating wave that hits one sensor and another sensor, the differences in phase are a result of the direction and the distance. So the angle and the distance. But if the response of each sensor is different, this also should be taken into account. Okay? So we have some assumptions that in a real environment, real product, maybe it's inaccurate. Okay? So this is also something that we assume that if the white noise gain is not too low, so if we increase the white noise gain, the sensitivity or robustness, okay, so the robustness of a beamformer to white noise gain, if we increase the white noise gain, so the robustness to white noise gain increases, which is good. But not only that, it is a common assumption or common knowledge that when we increase the white noise gain, the robustness to inaccuracies in the position of the sensors and the differences between sensors also increases. Okay? But there is no mathematical proof, but you can just try. You can try and see the correspondence between robustness to thermal noise and robustness to inaccuracies in the geometry of the array, okay, small differences, and also differences in the sensors. Okay, so it makes sense, but sometimes it's not direct. Okay? Because you think that if we design a beamformer such that it will be robust to white noise, how is it relevant to inaccuracies between the sensors and their position? But in fact, these inaccuracies, sometimes it is shown like noise. So it can be considered as noise. But if you want to prove it, you need to collect some data and make some random noise in the position of the sensors. So you change the position. So it's random. Instead of fixed position, you can randomly change the position. And you can also randomly change the response of each sensor, magnitude and phase, but with small amounts, not significant. And then this is equivalent to an additional amount of thermal noise, which is very beautiful, you see? Because when we design a system, we want that the design will be robust to inaccuracies, any inaccuracies that might be in actual environment and actual device. Okay? So think about that we design smart glasses, and of course we can put the microphones exactly where we wanted, but with the manufacturing process, maybe the positions are not accurate. So one thing is to measure the exact position of the sensors on each device, and put that in the design and include that, and also to measure the response of each sensor. So this is kind of calibration. Okay, so we make measurements, and the actual for each device we make these measurements, and then we design the beamformer and the rest of the algorithm of the processing. Howling control, the feedback suppression, all that. We design all that based on the measurements, and we need to put the exact beamformer and algorithms for each device. It will be different. So this is something that is very expensive to do. Okay? So sometimes you don't want to make calibration or design for each device, even though the devices may be different. So sometimes what you do is just you assume certain positions, you try to make that as accurate as possible, and then you increase the white noise gain. So it becomes less sensitive to other inaccuracies in practice. Okay, any questions so far? Okay, so how do we do that? How do we increase the response to white noise gain when we design beamformer that maximize the directivity factor? So what we do, we add an additional constraint that the white noise gain will be larger than a certain value, a certain threshold. And a good way to do that is, instead of minimizing this part here, or minimizing this part, we define a new correlation matrix that is actually a superposition. So we try to minimize, let's call it d alpha HF, or let's call it, no, we'll call it like this, because the directivity is the same. We will minimize the directivity for H with for H, okay? With a different correlation matrix, okay? So it will be, so it's not the directivity, okay? So it's directivity with weighted with some parameter alpha. So instead of maximizing the directivity, we will try to minimize. So it's actually not directivity, but let's say that we try to minimize, Okay. So instead of minimizing this or minimizing this, we will try to minimize superposition. Okay, a superposition of these two. We try to minimize the super. How do we do that? So we try to minimize something like that. H where gamma alpha is 1 minus alpha gamma 0 pi plus alpha im. You see, so if alpha is between 0 and 1, actually we try, instead of minimizing only this. So if alpha equals to 1, it means that we try to maximize the white noise gain. If alpha is 0, we try to maximize the directivity factor. So we try to maximize some superposition of these two with using alpha between 0 and 1. So this gives us some compromise or control over the trade-off between white noise gain and directivity factor using such a covariance. Okay? So it will be a measure that measures the correlation between them or the combination between them using some superposition. So this is a good way to control some trade-off. Whenever you have a trade-off and you try to minimize something and you try to minimize another thing and you have a trade-off between them, so just take something, combination. So maybe I can add additional things if I have other things that with a trade-off. So if you have a few terms with a trade-off between them, you can add parameters to give different weights to each one of them, and then you try to optimize. And this parameter will give you the trade-off between these kind of measures. And you see that because we know that when the white noise gain increases, the directivity decreases, and vice versa, so alpha is a parameter that if we increase it, so monotonically if we increase it, we give more weight to the white noise gain. And if we decrease it, we give more weight to the directivity factor. So it's like monotonically controls between these two measures, which is beautiful. So you see, with the multi-channel signal enhancement, we had a trade-off between noise reduction and signal distortion. Here, we don't have such a trade-off because we have this constraint. So we don't allow any distortion. So even without this distortion, we have a different type of trade-off between white noise gain and directivity factor using this kind of parameter. So don't restrict yourself to such a problem, but in reality, whatever you do in your research, try to find things. Sometimes you have a trade-off between different measures. How do you measure performance? How do you define? So for different applications, different problems, the performance measures will be different. And try to find which measures depend on other measures. If we have when we increase something, the other one decreases, and so on. So and then you can add some additional control parameters to control this trade-off. But also it's important to see that if it's monotonically, can we, if we decrease one, the other one will increase necessarily, or we can find other ways to control this trade-off. So it depends on the measure. So you need to prove something, okay? So try to analyze and explore these kind of trade-offs. the trade-off is not between two measures. You have additional, maybe 3 measures, maybe more, and you want to control them. So you can explore how to control in the best way this trade-off to achieve. What do we need? Okay? Because here we just wanted to design a beamformer, fixed beamformer, that will perform either in a diffuse noise environment or thermal noise. But we can add additional unknowns and see if we can control this performance, because the more that we add unknowns, and then we have something that is changed, we assume something, and then in a real environment it will be different, it will degrade the performance. So we can add additional parameters that control how much information we need, or how much this lack of information degrades the performance. And we can control or limit how much degradation of the performance we allow because of these unknown parameters or environment or whatever. Okay? So this is part of optimization. Okay, now let's assume that we have some directional interferences. How do we handle such additional information? So we said, for example, suppose that we have smart glasses and we have additional sources from the loudspeakers. So we have loudspeakers on the frame, and we don't want that it will create feedback. So if we have loudspeakers, and then the loudspeakers, these loudspeakers which are here, which are combined with the background noise, will come back at the output of the beamformer. So they will appear here. So we have feedback. And if we use the gain and so on, it will distort, or we'll get some howling sounds, which we want to avoid. So how do we add such information? So we call it null steering. Okay? So here we talked about max white noise gain, max DAF, and we have some trade-off between them. And now we talk about additional information. Okay, so the more information that you have, you can use it. Okay, so for null steering, we assume that we have some interferences that come from certain directions. Let's call these directions theta n, and 1, 2, and depends. So the more directions that we will try to cancel, the performance will degrade. What does it mean? So if we assume that we have interferences from some directions, and we design a beamformer that maximizes the white noise gain, so with additional constraint that we try to cancel a certain direction, source from a certain direction, what will happen to the white noise gain that we'll achieve using this beamformer? What do you think? To ask again, or the question is not clear, or after this you should know. It's after 10 days, you're experts. Yes? Exactly. Okay? So the more constraints that we add, we always know that with the optimization, what we want to achieve, it will be degraded, it will be lower. So if we add a constraint in addition to this, okay, this will always, for beamformer, any beamformer, we put this constraint, okay? And then we can add constraints, additional requirements. Constraints, we can call it additional requirements. Okay, so if we want to cancel any signal interference that comes from a certain direction, and we try to maximize the white noise gain, we find this beamformer, the white noise gain that is achieved, that maximizes the white noise gain, so the maximum white noise gain that is achieved with this additional constraint will be lower than that can be achieved without this constraint. The more constraints that we add, the maximum, the performance degrades. Okay? I can give you another requirement, for example. So, for example, a very common requirement is that to be robust to theta d. Okay? Suppose that I have theta d. So theta d, it means that I know the exact direction. And then I have some error in theta d. So what I will design the beamformer such that the beam pattern, the main beam, will be wider. So I can add some requirement that the width of the main beam will be wider. Why? Because if I don't know theta d exactly, I don't want that it will result in significant degradation, suppression of the desired signal. So I add requirement, additional requirement will degrade the performance. Okay? Always, when I add some requirements, it will degrade the performance. So my question is, why do I add requirements if it will degrade the performance? Why do I need to add a requirement, for example, to make the main beam wider if it will degrade the performance? Okay? So if we go to a real environment, and instead of theta d, suppose that I designed the beamformer for a specific theta d. And instead of theta d, in an actual environment, it will be theta 0, which is different than theta d. It will be a different angle. Okay? So if I design the beamformer exactly to theta d, and this angle, okay, so I wrote phi, just let's keep the notation, okay, theta d. So if I designed the beamformer with assuming that I know this theta d, so it will have good performance for theta d. But when this angle is incorrect, the performance will degrade sharply. Okay? On the other hand, if I design a beamformer such that is robust to these differences, so the robust beamformer, for theta d, the performance will be lower than the non-robust. But for theta 0, which is error in the angle, it will be better than the non-robust. Okay? So, in other words, what does it mean? Something that I talked throughout the course. That if we have some information, and the information is accurate, you don't need to design robust, whatever you design, robust beamformer to this information if it's accurate. But if it can be in a real environment with a mistake, with noise, it's inaccurate, it's better to design a robust beamformer to this error. And under this error, if you have error in the real environment, actually it will perform better when you have an error. So when you don't have an error, the non-robust will perform better. Of course. This is the way to work with robust optimization. Okay? And it's true for any optimization problems that you try to solve. Okay? Questions? Okay. So we want to add constraints such that we will cancel directional interferences from certain directions. By the way, we can also design beamformers which are robust to errors in these directions, which is beautiful. You see them. When you assume something, try to make it robust to errors. First, try to design the non-robust, solve the non-robust optimization problem. Then think what can go wrong in a real environment, what kind of errors can be added in a real environment, and then solve the robust optimization problem. Okay, so we're talking now a non-robust optimization problem. We know this information. We know this information, we know these directions of interferences. So we can add, just like we did with LCMV. Okay, so we have a matrix of constraints. Now this matrix will contain the steering vector in each column, steering vector regarding theta d. And for this steering vector, we need to get 1. This is like the distortionless constraint that we have with the LCMV. And for other directions that we want to cancel, we will put 0. So CHF, when we apply it to Y or to D, okay? When we apply it, when you apply it to H, this will give us the vector of constraints, like this, okay? So the first column in C, it's actually this constraint. The other columns are the constraints and interferences from other directions. And of course, you can play with these values. Maybe you don't want to put here exactly 0. You can put anything that you want. But this is the simplest way. So when we have this matrix of constraints, we know how to solve it. So we need to find the beamformer, either that maximizes the white noise gain under these constraints. We can find the beamformer that maximizes the directivity under these constraints. Or if we want that the beamformer will be robust. When I say robust, robust to what? Robust to thermal noise. We can try to minimize this under these constraints. See? We take everything into account. Everything that we want to take, we can take into account. Questions? Now, you see, formulation of a problem, understanding what can be wrong, what can be inaccurate, what are the assumptions. This is the main objective. You know, this is when you do research, and you formulate correctly the problem and you understand what are the assumptions, what can go wrong, what can be different. This is the most important. Afterwards, because if you make mistakes in that stage, you cannot fix it afterwards. Okay, you can fix it if you go back. But this is the most important, to formulate the problem. Afterwards, it's much easier to continue. And also to make smart approximations. Okay, so now we defined everything, actually. Now I don't need to tell you the solution because it's easy. You know how to solve it. So you know how to minimize here what is inside under these constraints. We know how to minimize this under this constraint. We know how to minimize this under constraint. Because we learned how to solve such a problem with the LCMV. Similar. So we can use that. We can use what we did. So we know how to solve that. The optimization problem, we know how to solve such an optimization problem. So here, if we try to maximize the white noise gain, subject to this constraint, we will get this solution. So we can call it minimum norm beamformer. Because it's the minimum norm of this solution, but you can call it whatever you like. You can call it max white noise gain with linear constraints. You can invent new names, whatever you like, but try to make it simple and reasonable, okay? So let's call it minimum norm, because it's actually the minimum norm of the constraint. You see, what is this? This is the norm of the beamformer. You see? We take the summation of the magnitude squared. So when we have minimization of norm, so it's the minimum norm of this constraint. That's why we call it minimum norm. Makes sense. Okay, so instead of this, we can define a different problem. We can define, let's maximize what? The directivity factor with this constraint. So we can call it something. We can call it null steering. If you like a different name, you can give a different. So we will call it null steering. So this is the solution. And of course, you see that also here, okay? When we design a beamformer with additional constraints, the white noise gain that is achieved during this, using this beamformer is smaller than the one without these constraints. So if we use only the regular constraint and the beamformer here, we get the delay in sum. Because the beamformer that achieves maximum white noise gain using this constraint I don't even need to mention. Once I tell you to find the beamformer, you have this constraint. Distortionless response towards a desired direction. This is always, when I say find the beamformer, you have this constraint, that no distortion towards a certain direction. Now, this beamformer is the delay in sum. So the white noise gain that is achieved with white noise with the delay in sum is always larger than with that achieved with minimum norm. Of course, because here we added constraint. So the white noise gain is smaller. This is what we mentioned. Now, if we have the null steering beamformer that is achieved with additional constraints and interfering directions, it will be smaller than that achieved without these additional constraints with the max DF beamformer. Okay? So all this makes sense, you know, intuitively. If you like, try to prove it, which is also nice. Things, sometimes, when you do your research, I told you, it's very important to think intuitively. What is expected? What the result? How something affects the performance or results or whatever. Try to think intuitively and then verify it with mathematical derivation. If you are able to prove it, great. If you get different result, then it's also, don't skip and say, oh, my intuition is bad. On the contrary, this is something that you can learn. Because if by intuition you expect for something and in reality you get a different result, this is a very interesting result that should be explored. Because it means that you can learn from such contradiction between intuition and the result. Okay? Unless it's just implementation error. And then it's just a bug in the algorithm or you did something wrong. Also, it's something that you can learn. But if there are no bugs and you get results in your research that contradicts your intuition, this is the place where you can improve your understanding and you can make progress in your research. So it's very important. Remember, sometimes I ask you questions and you answer something which is wrong. And I tell you, this is very important. So don't be afraid to reply with something which is wrong, because then it means that you give an answer, and according to your intuition, you said a certain answer. So and then if the true answer is different, so you understand, okay, my intuition contradicts with the expected result, so I can learn. This is something that is important. I can learn from it why my intuition was that and why the result is different. Okay, so always don't try immediately to find the true answer. Try to think, what do I expect that the answer will be? Based on my intuition, based on understanding so far. And then continue. Okay, because it's very important to find these such contradictions. We learn from contradictions. You know, also with machine learning, we learn from contradictions, from wrong or false performances or misdetection or whatever we find. There is something which is called reinforcement learning, okay, machine learning, and all that. So it's also with machines and algorithms. It's the same. It's the same. Also in life, we learn from experiences. Okay, and of course, we can minimize this part, which means that we find a robust beamformer, which controls the trade-off between white noise gain and directivity factor, subject to the constraint, subject to this constraint, matrix constraint nulls, and then we get this solution. So you see, the mathematical derivation is very easy. Once you understand the problem, you define it. Let's see, I know that you need to go to a break, but just I want to show an example, and then we'll have the same 10 minutes break. Okay? I will not keep you. Example. So suppose that we want to employ the minimum norm null steering slash, which be, if we take a parameter alpha, just like here, so we have both of them as special cases. So if alpha equals to 1, we have the minimum norm. If alpha is 0, we take the null steering. Okay? So let's try to find this beamformer with constraints on directions. So the desired direction will be 0 from the end fire, if we talk about linear array. And then we have interferences from 45 degrees and 90 degrees. And the distance between two elements is 1 centimeter. And we can change the number of sensors. Okay? So of course, the more sensors that we get, we will improve the performance. Makes sense, because we use more information. And let's see the performances as a function of alpha. So what do we expect intuitively? If we increase alpha, what will happen to the white noise gain? It will increase. What will happen to the directivity factor? Decrease, exactly. What will happen to the beam pattern? This is a nice question. What will happen to the beam pattern as a function of alpha? It's an interesting question, okay? Okay, very good, very good. The main beam will be broader. Okay, yes, very good, very good. Because when we increase alpha, we increase the robustness to white noise gain. The white noise gain will increase, so the directivity factor decreases. So the directivity factor decreases, it means that the main beam will be wider, will increase. Very good. What will happen to the beam pattern at the direction theta d, theta 1, theta 2 as a function of alpha? Okay, the beam pattern. What will be the response, or the value of the beam pattern, the power beam pattern, for these directions? How does it depend on alpha? What do you think? should it depend on alpha? You see the constraints? This is the constraint matrix. So when we design this beamformer, we have these constraints. So the response for theta d, what should it be? The beam pattern for theta d, what should it be? Should be 1. This is the constraint. The response for the direction theta 1, 45 degrees, what should it be? 0. The response to 90 degrees? 0. So it doesn't depend on alpha. Okay? So let's see that. Okay? So of course we can see the white noise gain for different, but I just want you to show you the additional information. The beam pattern. Okay. So we have the beam patterns for alpha, which is small. You see 1, 10 to the power of minus 5. Very small. With 8 sensors. And here we have for different frequencies. This is for 1 kilohertz, 2 kilohertz, 4 kilohertz, 8 kilohertz. Okay? So you see when we increase the frequency, what happens to the main beam? The width decreases. Makes sense. When we increase the frequency, usually if we don't have aliasing, what happens to the directivity factor? Increases. Okay? Because we have more narrow main beam. So the directivity increases if we don't have aliasing. If we have aliasing, we will start to see some side lobes increase. So the directivity factor will decrease. Okay? Now, this is for small alpha. Okay? Now I increase alpha. If I increase alpha, the white noise gain increases. The directivity factor decreases, which means that the main beam will be wider. Okay? Let's increase alpha to 10 to the power of minus 3. Okay? So if I show you this, 10 to the power of 3, this is before, this is after we increase. You see? The main beam increases because the directivity factor decreases. Let's continue. Let's make it even larger. Make it 1. Make it 1, and you see it's even wider. And what happens? Okay. Okay, this is 10 to the power minus 5 alpha, very small alpha. This is 10 to the power minus 3. So we just increased the width of the beam, main beam, which decreases the directivity factor. Now if we further increase it, to alpha equals to 1, you see that the main beam becomes wider, but also we may have some side lobe, especially for low frequencies, some side lobes that even larger, that give a larger directional gain for other directions, which is not good. Which means that the beamformer that maximizes the white noise gain can decrease significantly also the directivity factor. But still, the integral over all directions is still larger than 1. Okay, so if you take the ratio between the gain in the desired direction and the integral, it's still larger than 1, which means that it doesn't amplify the diffuse noise if the noise comes from all other directions. But if noise comes from this direction, 180 degrees, it will decrease it. Okay? It will not decrease the average noise that comes from all directions. It doesn't mean that it will not increase or amplify noise for directional noise. So we added directional suppression from certain directions. Which directions? 45 and 90 degrees. So you see in all these beam patterns, for 45 and 90 degrees, we have nulls. All frequencies and all alpha. You see, if we take this alpha, 45 degrees, we have null. 90 degrees, we have null. For all alpha and for all frequencies, because this is part of the constraint. But because we added this constraint on 45 degrees and 90 degrees, it chose the optimization solution, chose that for alpha equals to 1, it chose to amplify this direction. Because under this constraint, we didn't have any constraint on 180 degrees. Okay? So you see how beautiful it is when you understand. When you understand the requirement, when you understand the assumption, when you understand the results, and you check how the results correspond to what you try to solve. And you know, in mathematics and signal processing, when you try to solve problem, so the solution will be as good as what you define the problem. You don't expect to get better results than what you define, than what you require. Okay? So, any questions? We'll have 10 minutes break.